Good afternoon, everyone. I'm Michael Kouremetis. This is Dean Lawrence. We are two members of a team called Mirage at the MITRE Corporation. Our third member is Ron Alford, but we left him at home. He's the troublemaker. If you look at our backgrounds, right, we come from a bunch of different fields. I actually sit in the cyber labs. Dean sits in the software labs. Ron actually sits in the AI labs. But one of the cool things we get to do at MITRE is we have a big research portfolio that we can pitch and pursue research at MITRE. And we get to pool engineers and researchers and scientists from everyone in the company. So today we're going to brief on a project we did, or it's still ongoing, but we started last year called Mirage, where we basically got together and started asking questions about future cyber adversaries. We had a focus on, or an interest, we have interest outside of AI, or excuse me, outside of cyber and autonomy. And so we began to ask questions about, well, if we see autonomy in an adversary, what's it going to look like? And what kind of, or what's the, on the other side, on the defense side, what are we going to need to do to counter that? So that's how all this work began. I'm going to continue to set the scene and walk through how we got to a hypothesis, and something to test and to build, and then I'm going to give it to Dean, and Dean's going to go over actual implementation, because we built all this and then ran experiments, and then we'll talk about the results. All right. So I mentioned autonomy, and specifically autonomous cyber adversaries. Autonomy is a pretty overloaded word these days, so we have a quick definition here so that you know what we're talking about when we say autonomous cyber adversary. To us, simply, an autonomous cyber adversary is one where there's really no human operator in the loop. We think, or today we see a lot of autonomy of action, right? Actions can be executed autonomously, whether defensive or offensively right now. But from a decision standpoint, we don't see a lot of autonomy of decision, or autonomy of real decision. So on the level of a top-tier red team operator, right? So when we think about, or we say, excuse me, when we say cyber autonomy or autonomous cyber adversary, we're really trying to think about an adversary or attack or campaign, whatever it be, that doesn't have a human in the loop and really has an artificially intelligent agent behind it, right? And it's doing it from start to finish, doing the operation, the campaign. Oop, wrong way. So when we have that working definition of autonomous cyber adversary, we began to start to have fun and think about what are the big game-changing capabilities that this adversary could have, and what would they mean for what our current defenses are now. There's actually a lot, right? You can go pretty wide on what these adversaries may have. We kind of dialed down on speed, scale, and flexibility. I'm not going to go through these, but we began to ask questions like, okay, what if a whole campaign takes a matter of seconds or microseconds, right? Assuming there's not any delay with some sort of exfiltration objective or taking files. But if it's over and done in seconds, what does this mean for analytics, right? I mean, the sensors haven't even sent the logs to the aggregation, whatever that may be, the data lake, and analytics haven't even run. Or scale. How long does it take you to train your best red team operator? How many years of experience? How many engagements is that until they're top notch? What if I take those years and do it towards developing an autonomous adversary, which might take me 2 years, might take me 5 years, but once I have that one autonomous adversary, I can make a copy of it, right? That's why we like software. It scales pretty quickly. And also flexibility. This is a trait that we will always have with human operators, right? For now, innovation and creativity is a human thing. But also we'll see some flexibility that will be a little bit different, right, than when we see in a human operator. Instead of shelves of exploits, maybe we have shelves of AI models that the adversary has, and they're going to be swapping them out and using them. So stuff like that. Right at this point, I'm talking about AI. I'm 3 assumptions deep. Of course, I land on Skynet. But the point being that, in a serious note, there could be some capabilities, right? They're going to be real game changers, and just a total mismatch for what we're doing or defensively right now. keep going the wrong way. So what do we do? If we're trying to think about this future adversary and potentially cut it off or try to make defenses for when and if it comes along, we were in a room talking about this, and we're like, well, there's just, these capabilities are just so asymmetric, right? On time and scale to what we have now. They're active, they're reflexive and responsive. And so essentially our colleagues in the deception department at MITRE overheard us, and they're like, essentially we were saying their trigger words. And so we're like, okay. They're like, what about deception? And so we're like, okay. Deception is intrinsically has a lot of these things that we were saying that this adversary would have, right? It's asymmetric. It turns the table, right? Instead of your SOC analyst trying to figure out who the bad guy is, the bad guys are trying to figure out what don't I touch, right? So I don't alert. It's also very interesting because it can be very targeted, right? We actually have a framework for this, right, called MITRE Engage, where we know how to engage with an adversary. So we really liked that, and we thought it was very promising that, as a high level, theoretically, with cyber deception, we could engage with a potential autonomous adversary and try to target it. And again, it was asymmetric, right, where we could try to attack it. So we land on deception. Like, okay, let's go with the deception, but how are we going to do this, right? How are we going to attack whatever, or counter this envisioned, autonomous cyber adversary that doesn't even exist yet? So we went back to, the science, right, and what we see right now in AI. Turns out there's a lot we think that such an adversary would have. Here are the few domains that we have. We like autonomy, and that's what we kind of started out as. So we're going to focus in on automated planning and search, right? Two very promising areas in AI, most commonly associated with the algorithm, right, AlphaZero, that beat the Go champion. And also, they generalized it right now, it can be applied to many domains. So like, okay, if we're thinking now, what are the current state of autonomy? Where's it at? What can it do? And we're going to assume this future adversary is going to take and build on that. So if you've ever read an AI textbook or any automated planning, there's a lot of algorithms, a lot of approaches, but a lot of them have really common tactics, right, or strategies or concepts or whatever you want to call them. One of the biggest problems, right, in planning as a field is state space, right? Anything beyond a simple robot in a closed room trying to do something has a state explosion, right? Because they have to sense the environment, determine what actions they want to do those actions, and hopefully it leads them to where they want to do. This is not at all unique to the cyber problem or the cyber attack problem. But if an adversary were to attack, right, our network, our system, it's a pretty complex problem, right? So we're fairly confident that they're going to be doing state space reduction. So that's one strategy they're going to use. They're also going to do online planning. This is also pretty intuitive, right? Has anyone ever pen tested, right? And they figured out the entire plan beforehand and nothing had to change, right? So you're not going to have this a priori planning. You might have an AI agent have a plan, but it's quickly going to go out the window, and it's going to need the ability to replan. And then lastly, goal-oriented. Also very common in planning and search problems to gear an agent orient an agent towards its objectives, whether you have one objective or many objectives with sub-objectives. But the cool thing here is we know what the objectives are for a cyber adversary. Even if it does have an artificial intelligent agent behind it, it's going to have the same objectives as human operators, right? So it's going to want to get persistence, laterally move, do exfiltration, and have grand goals, grand campaign goals that we can also play to. So we're making strong assumptions, but we're pretty confident that this is what an adversary would be relying on to do planning and search for their autonomous capability. So if we want to counter this, how do we do it? Well, at a basic level, we're just going to try to do everything that it wants to do and try to prevent that or make it worse. If they're going to try to reduce state space, we're going to try to expand it. Either from a perception standpoint or in reality, right? Maybe I tell the agent that there's 25 additional hosts, but they're not there. or I actually have honeypots there. And they're not going to lead to anything important, right? Very common from deception practices already. Planning. We can't really stop an agent from replanning, but we could potentially induce it to plan a lot more than it has to and make it slower and make it cost more time, which is very important if we also want to be able to track it or detect it. Goal satisfaction. Again, we can't change its goals, but we know its goals, so we can apply deception here as well. The key difference being we're really going to try to create deception that's going to attack the underlying planning algorithms and kind of get them in logic loops, right, where there's nothing preventing the agent from going somewhere else, but they keep getting stuck in their mode of planning, and they can't figure out what to do. So at this point, there we go. We've kind of reached our hypothesis, right? And we have something that we can go off of to build and to test. So we want to try out these theories we have about deception, potentially create novel deceptions, and then we also have to figure out how to make something that resembles an autonomous adversary and put it all in a range and then test it, right, and see how it does. And we're also, in addition to just looking at deceptions outright, we also want to look at how effective, right, or what the efficacy of this overall system is. One of the mandates we have at MITRE is that, right, any research, the goal is eventually for it to be transitioned, to be out there, to be in use. So if we build this prototype and it's great, but we can't ever see it being practical, right, for actually testing deceptions and deploying them in production, why are we doing it? Or we should pivot. But with that, I'm going to toss it to Dean to actually get into the fun stuff.
Yeah, so now we know that the goals of what we're going to build, we can start to collect the necessary components to construct this system for evaluating the effect of deception against autonomous cyber adversaries. So obviously, we need cyber adversaries. They ground the problem and make it understandable to what specifically we're fighting against. We need autonomous agents to run those adversaries. They need to run many of the things that we just talked about. We need novel cyber deceptions that specifically target those algorithms. And then of course, we need a cyber range in which we can deploy all this stuff and run it against each other and see what the effects of it actually are. So there's been a lot of existing research in a lot of these fields. So there's been several projects in the realm of deception and kind of automatic placement of deception, stuff like SODA and Chimera. And then in the realm of automated evaluation evaluation of automated adversaries, both between simulation and emulation. You have stuff like Microsoft Cyber Battle Sim, which had been extended by some researchers to include some deception work. And then you also have Cyborg that can straddle the line between simulation and emulation. And then you have some evaluation that goes all the way into the realm of emulation, like Cygil. So this work that we primarily did last year and that we're presenting to you now kind of sat in the region of emulation with high-quality red agents and deception as a core component. Pretty much a relatively unique position to be in. So to start off, for our adversaries, I don't know if for those of you that are unfamiliar with Caldera, Caldera is a free and open source autonomous adversary emulation platform developed and maintained at MITRE. So it's publicly accessible on GitHub. You can go clone it now. It's basically for the ease of teaching and allowing users to deploy and run adversary emulation basically at the click of a button. So it's helpful that Caldera is highly modular and extensible. So it's very easy to implement new adversaries. And for our case, it's particularly easy to also swap out autonomous planning strategies. So there's code within Caldera that allows you to swap out the logic in which it allows it to make its decisions about which actions to pick next. And we're able to utilize that to kind of implement some of the things that which we've talked about. So within that, we've implemented two adversaries for this work. One is a simple exfiltration adversary that laterally moves and basically exfils files back to the Caldera C2 server. And the other is an implementation of a PowerShell-based ransomware called Black Sun. And of course, we need our agents. This is the algorithms in which we're going to be attempting to evaluate. So we chose three. The first of which is called atomic, and this is the default Caldera behavior. It's really not intelligent. It's basically taking the actions that it knows that it is able to do at the moment and then executing them in a defined order. We then have look ahead, which begins to introduce reward and future expected reward into the equation. So the look ahead planner is able to evaluate the reward of each action it has access to, and then select the action at which it expects to receive the highest reward from. And then we have the guided planner, which constructs a guided dependency graph between actions in which it can find the shortest path from the current position it's in to its goal state and execute the actions along the way. And just to reiterate, these capabilities are also all publicly accessible and can be toyed around with if you are interested. So now we need novel cyber deceptions. So in previous research, in previous years, we had explored what we call static deceptions. And these kind of take the form of fake user credentials or fake hosts on a network. And generally, these might be more understandable under the term honey artifacts, if you've heard of those. But the general effect of them is that they explode the search space of the adversary. So it makes it take way more actions it has access to, but ultimately it's not a particularly difficult thing to combat. So it's not difficult for an adversary to have logic in it that deprioritizes information if it learns it to be not helpful. So if it attempts to use user credentials that don't work the first time it uses them, it's not hard to figure out that maybe don't use those again. And it's not hard to kind of chop that tree, that branch off the tree. So what we looked at for doing for this year was what we call dynamic deceptions. And the goal of these is to introduce inconsistent underlying state into the environment. So this one example of this, and something we implemented to kind of combat ransomware and exfiltration, was imagine that you have an agent that's going around attempting to discover what files are in a system. So it might execute an LS or a get child item in PowerShell. You can then have a separate service watching for that activity, and if it observes potentially adversarial activity of this variety, it can execute its own deceptive actions directly in response to those actions taken by the adversary. So this might be in the case of an LS, it might go through and change the file names of many of the files that the agent just discovered. This then means that the agent now has some knowledge within its knowledge base that no longer corresponds to the true state of the environment. So in order to do this, we built a Windows service that is modular and allows you to kind of plug in and allow you to configure these different triggers depending on what kind of activity you want it to be to respond to. So back to the example with our PowerShell actions, if you do a get child item on a specific honey directory that we know nobody should really be looking at, we can then decide, let's change some or all of the file names that agent just discovered, so that the next time they try to then go and move those files or exfiltrate them, its actions inexplicably fail. And it continues to do this in a way that ideally would really confuse it. And then finally, we need a place to test all this stuff. So to do that, we can introduce Caldera Range. So Caldera Range is a Caldera plugin implemented in collaboration between the Caldera team and the Center for Threat-Informed Defense. It's pretty much just for standing up infrastructure in an automated and rapid fashion in the cloud between AWS or Azure or on-prem. And it's really tightly coupled and highly automated for standing up specified infrastructure and populating it in a lived-in fashion, so that we can tear it down, stand it back up, have everything installed in it, and just run Caldera, because it'll pre-install our implants and let everything run. Back one.
Did it go? There you go.
So now that we have all of that, we can kind of put it together into a coherent system that allows us to begin evaluating this stuff. So to do that, we put together a pretty simple experimentation program. This took the form of a 2x3x4 factorial design. So we had 2 cyber adversaries, 3 attack planners, and then 4 deceptions, including the baseline of no deception. And this ended up being pretty light for a few reasons. one of which we didn't have a fully automated fashion to stand all this stuff up. We still needed a person to kind of hit go on some things. We ran this all in emulation, which we found to be slow and not quite up to speed of what we would need to really evaluate this stuff at scale, at the scales that we somewhat wanted to. And we were fairly time-boxed in this research effort. So we had a deadline, and we had to accomplish our goals within that deadline. So we only executed about 3 games per combination of factors for a total of 72 games. And within that, we tracked a number of metrics. So what we're primarily looking for is to look at what deleterious effects did it have on the ability to plan. So because actions that Caldera is taking are atomic and they're discrete, you can kind of check how many actions failed that it took, how many were repeated, how many times did it have to do the same action twice, and not expect the result of that. You can also do things about how much information it learned. So Caldera tracks what we call facts, which are the discrete units of knowledge that Caldera discovers over the course of a game. So that might be a file path or a password. Or you can do overall larger things like total runtime. And all of this stuff was directly derived from Caldera operation reports, which you get at the end of each game. And back over to Michael to talk about the results.
Cool. So again, we were after 2 things. Did the deceptions work for our novel deceptions we created? And what do we think of the entire system? Is it something we can keep to build on and actually transition one day and do for production environments, or should we pivot? Suspense, all good. Our chief of research did not find that amusing. But anyways, so results of the cyber deceptions. We'll tackle the cyber deceptions first. I know you guys can't read this, but it's essentially we have 3 of the axes are different metrics that Dean just went over. So if you can see the blue dots were the games with no deception. And so the very performant, or the most performance you can be is in those top corners. So we were pretty surprised to see that it was, visually you can cluster, right, or separate the different classes of deceptions pretty well without really any post-processing of the data or smoothing or anything like that. But what you see is the deceptions at the bottom and then the no deception at the top. You can look at this later, but we're going to break it down for you here. So we saw 2 things. One, the general conclusions we took from it is that all the deceptions we did have a negative performance, which is good. And then also kind of a straw man evaluation of were the advanced planners that we have actually smarter than the baseline planner? Because that would have been bad if it wasn't the case. We did see that though, so that was a good sign that we could kind of lend more credence to our results. And then we had very specific things that we saw that really dialed in on the planner implementation. I'm not going to go over these, but what we took away from it and reminded us is that this autonomous adversary, the algorithms they're using will be software, they will be written by humans. And so deceptions that we do have are going to have quirks, right, and idiosyncrasies that we're not going to expect, whether good or bad. But we did find that here where certain things happened, and we're like, oh, why did it do that? And it really tied into the implementation, right, that we had, much or less so than the deception that we did. All right, so that was deceptions, or the specific deceptions we did in kind of like the limited experimentation program. But how do we feel about the entire system? So we've got some radar plots here. This is pseudoscience. These are our feelings about the system. So you're welcome to come debate with us afterwards. But we looked at it from kind of two sides. Modularity and scalability, like could we do more experiments, do more deceptions, more planners? And then also practicality, how realistic were our experiments? So for modularity, you could probably guess, right, that deceptions and planners take a lot of effort to make. And we didn't really see a way of automating that or kind of increasing or decreasing that time. And also experimentation, like Dean mentioned. We don't work in cloud too much in infrastructure, so we weren't sure exactly how quickly or not these experiments would be, and they were quicker and much more efficient than manually doing them. but they're nothing on the scale of like simulation, right? So if we want to simulate 1 million games, that's something we can't do from an emulation perspective. On the practicality side, our deceptions were real. We liked our metrics. Our ranges were real. The experiments themselves, our cyber range was a little simple, so it could be more complex. And the same thing with our planners, right? What we implemented were like, the very simple variants of some of the major algorithms that you see in the planning space. So would love to build that out more and make it more practical of what we think an actual well-funded, well-resourced autonomous adversary would have. So with that, that's the end of our work for this past year. So you might be wondering, what are we doing now? Well, we've continued to work on Mirage, and we've essentially shifted left to simulation. So currently in development, we are actually trying to do everything we did and get parity within a simulation. We were skeptical, as obviously we lose fidelity when we go to the simulation. However, we've been able to work with other teams that are also working on a very high fidelity cyber simulation. So the goal is we can bring it over in the simulation, do way more experiments, way more runs, and build out the planning algorithms for spending the dev effort on the planning algorithms, because everything else should be easier. But with that, I think that's all we got. So thanks. I guess we got 3 minutes. Do you want to take questions?
Sure.
Okay.
Yeah.
Is there any questions? I can't see.
Test, test.
There we go.
Yeah, I got a question. At the beginning of your presentation, you outlined a number of search algorithms. Did you consider the notion that a novel algorithm would be used or discovered by the AI itself? And how would that affect your assumptions of this particular study?
Sure. So when we did consider it, it was a mix of what's out there now that, we want to limit our assumptions, right? So if there's something unknown that's going to come out, we weren't going to go off of that. So we're kind of going on of what we saw today now in these planning algorithms. But yeah, it would be very interesting if a new algorithm came out or AI found a better algorithm for how it would work. I don't think we would, it would possibly break assumptions right under deceptions, right? Because we started with current algorithms, what they use, and then built the deceptions for that. So obviously, if there's another algorithm, deceptions might be meaningless for them, right?
Right. I'm not sure if it's parallel, but in the AlphaGo example, I believe there were new strategies discovered for defeating Go. And I'm just wondering if new strategies would be discovered for search, thereby creating a problem with the original assumptions of the...
Right. And then so one of the assumptions is what's the most near term, right? And so we saw okay, there's a generalized AlphaZero, right, algorithm. These search algorithms that we mentioned, they do exist right in PDDL, planning domain language. They're implemented. Someone can take them and use them. So we just went with that's the kind of the lowest level of effort for what we would see an autonomous adversary trying to do first. But
right.
yeah,
Thank you.
Yeah,
Thank you.
Definitely.
As a former user of Caldera and kind of the research you've done now, how do you envision improving the time complexity of the operations? You said running 72 simulations isn't really realistic for, I guess, a simulation environment. So how do we improve that? Ensure that we can do thousands and thousands of test cases to kind of make this research viable for all adversary deception.
So let me ask, are you restricting to staying in emulation world and not going to simulation? How do we do lots of experiments with emulation?
Sure.
You want to take that one?
Well, there's scale problems. So I think
right.
from one perspective, as devs on Caldera, we're aware of different issues we've run into over the time of just when you're working with larger systems, the kind of runtime explodes in certain ways. So I, in particular, have done a lot of work in just let's make Caldera faster. But obviously, I don't think that's a full solution. to that. I think obviously there is runtime improvement work to be done, but in terms of as a fundamental issue, I'm not sure that we have a great answer for doing this in emulation.
Yeah, I mean, we're not going to do research on how to make infrastructure, right, set up faster. I think our biggest thing was, okay, it took us a couple months to write one of these exceptions last time, and now when we're porting it now to the simulation, we have an API, right? So we're just coding effects, and we don't have to test anything like that. So we do get the speed up there. We've also thought of the simulation as being a precursor to the emulation, right? So run 10 million experiments in a simulated environment, take what's most promising, and then we move that to emulation, right, and go from there.
Cool. Let's talk offline.
Yeah, thanks.
I think we're out.
Cool. Yeah, I think we're done. Thanks, guys.